Welcome to the AI Research Roundup. I'm Alex. Today, we're looking at a paper from the Hugging Face trending list, published on February 10, 2026, just a couple of days ago. It introduces the P1-VL family of models, which are the first open-source vision language models to secure 12 gold medals on the rigorous high PHO physics benchmark. The paper is titled P1-VL, Bridging Visual Perception and Scientific Reasoning in Physics Olympiads. And as we'll see later, when combined with a multi-agent framework, this system actually achieves the number 2 rank globally, surpassing proprietary giants like GPT-5.2. And for those interested in the implementation, the authors have shared their code on GitHub. Figure 1 highlights performance on the High School Physics Olympiad benchmark. Solid bars represent open-source models, and hatched bars indicate closed-source ones. The flagship P1-VL 235B model, shown in the fourth bar, achieves a score of 39.3. But notice the second bar. When augmented with the Physics Minions agent framework, the score rises to 40.9, securing the number 2 spot globally. Even the compact 30B model, further right, delivers a strong 35.0, beating several larger competitors. To understand the difficulty here, Figure 2 displays a sample problem from the 2025 International Physics Olympiad. It discusses the forces acting on champagne bubbles, providing standard formulas for density and pressure in the text. But notice that the text alone is insufficient. To calculate the viscosity, the model must visually analyze the train of bubbles photographed at the bottom. It needs to measure the radius and the vertical distance between bubbles using the millimeter scale, just like a human student would. This illustrates a constitutive diagram, where the visual component holds essential data that is completely absent from the text. So to enable this kind of multimodal reasoning, the team built a custom dataset, summarized here in Table 1. It consists of over 8,000 problems collected from 20 textbooks and nearly 200 Olympiad sets. As the data composition section shows, the mix is balanced roughly 50-50 between competition problems and textbook exercises. Most importantly, the images statistics at the bottom reveal that over 5,500 questions contain images, ensuring the model is heavily trained on visual-dependent tasks. Alright, Figure 6 visualizes the training dynamics using curriculum reinforcement learning, where the model faces progressively harder tasks. The top row follows the 30B model, and the bottom row the 235B model. On the left, we see the average response length climbing across the 3 stages, which means the model is learning to think longer and generate deeper reasoning chains. Matching this, the graphs on the right show that as the model takes more time to reason, its overall score on the physics benchmark consistently trends upward. Table 3 breaks down these results across the 13 specific exams, ranging from the International Physics Olympiad to regional competitions like the Pan American Physics Olympiad. The columns here track scores for each event, with the final averages and medal counts listed on the far right. Looking at the second row of the model rankings, the agent-augmented P1-VL system hits an average score of 40.9, which secures the number 2 spot globally, just ahead of GPT-5.2. 2 rows down, the standalone 235B model also performs exceptionally well, earning 12 gold medals and an average of 39.3 without any external agent framework. So, while Table 3 focused purely on physics, Table 4 addresses a critical question. Does specialized training compromise general scientific reasoning? To find out, the authors evaluate the models on the Frontier Science Olympiad benchmark, which spans biology and chemistry. Looking at the highlighted row, the agent-augmented P1-VL system achieves a total score of 67.1. This secures the top spot among open-source models, surpassing general-purpose heavyweights like Grok 4 and DeepSeek V3.2. Moreover, comparisons with the base models at the bottom reveal an improvement of roughly 8 to 9 points, proving that learning physics transfers positively to broader STEM tasks. Wrapping up, 2 takeaways stand out. P1-VL effectively bridges the visual logical gap by treating diagrams as essential constraints rather than just illustrations. Furthermore, its high ranking proves that open source models can now rival proprietary giants in rigorous scientific reasoning. This marks a significant step toward general-purpose physical intelligence. That's it for this episode of the AI Research Roundup. I'm Alex. Thanks for listening.